Hello everyone, I'm Hanlin from Tsinghua University, and today I'm going to present my joint work with Yong on a faster construction algorithm for distance sensitivity oracles. First, what are distance sensitivity oracles? Suppose you have a directed graph. You want to build a data structure on this graph that supports the following kind of query. In the query, you are given three vertices A, B, and X. You want to find the shortest path from A to B that does not go through X. So the answer is the blue path in our example. This is a natural and well-studied problem in graph algorithms. For example, consider a communication network where the nodes are computers and the links are the communication channels between computers. So crash failures are unavoidable in such networks. Let's suppose you want to send a package from computer A to computer B, but computer X somehow crashed. So your task is to find the shortest path from A to B that does not go through X. This is exactly the DSO problem. The DSO problem was studied heavily in previous work. The naive algorithm is to pre-compute the answer for every possible query. The space complexity is n cubed, and query time is a constant. Dimitrescu et al. Showed that the space complexity can be reduced to n squared while maintaining the query time constant. Unfortunately, their DSO requires roughly mn squared time to preprocess. This time bound is kind of too large even for moderately sized graph. And later, Bernstein and Kager improved the preprocessing time to roughly mn. Even for the outpath shortest path problem, we only know how to solve APSP in total mn time, and it's conjectured that there are no much better algorithm for APSP. Since DSO is no easier than APSP, we can say this mn time bound is nearly optimal. So are we done now? Actually, there is still a quite interesting parameter regime for us to explore. That is unweighted graphs. In unweighted graphs, APSP can be computed in roughly n to 2.5 to a6 time using fast matrix multiplication. So it could be possible that DSOs can be also constructed in some time bound faster than n cube, also using fast matrix multiplication. This direction was also considered in a line of work. The first question is whether we can achieve subcubic preprocessing time. This was studied by Wayman and User, and they give a DSO with preprocessing time n to 1 minus alpha plus omega and query time n to 1 plus alpha. Here, omega is a matrix multiplication exponent, and alpha is some parameter that you choose. Notice that the query time here is n to 1 plus alpha, which is superlinear. Can we achieve sublinear query time? Grandoni and Williams showed the answer is also yes. Their DSO has preprocessing time of this form and query time n to 1 minus alpha. The point is that if you choose choose a suitable alpha, then the preprocessing time is subcubic and query time is sublinear simultaneously. Still, the query time for the oracles by Dimitrescu et al. And Bernstein and Kager, they are all constant query time. So it's natural to ask if we could also achieve constant query time in this regime. This was recently studied by Chechik and Cohen, and independently by myself. In particular, my ESA paper showed a DSO with preprocessing time n to 2.7233 and constant query time. So let's review the preprocessing time of the previous DSOs. Even if we assume omega is equal to 2, the preprocessing times are n to 8 over 3, n to 14 over 5, and n to 8 over 3 respectively. Seems that we are stuck at n to 8 over 3, and it's natural to ask whether this n to 8 over 3 is optimal or whether we could do something better. Let me mention that there are many other problems that are solvable by fast matrix multiplication and have seen some progress. For example, the Alpers bottleneck path problem and the Alpers non-decreasing path problem. For both the problems, initially we know some slightly subcubic algorithm by fast matrix multiplication, and then a sequence of work improved the algorithm finally to something like n to 2.5. So would a same story happen for DSO? Yes, this is what we achieved in our work. We show that there is a DSO with n to 2.5794 preprocessing time and constant query time. We improve all of the previous results and break the n to 803 barrier. Typically, for such kind of improvement, we need some new algorithmic ideas. So the most significant new idea is to use a joint of symbolic adjacency matrix. Actually, I would say this is a quite classical idea in shortest path, but this is what we need to beat the n to 803 barrier and obtain something closer to n to 2.5. We also need the previous technique of bootstrapping the DSOs in my previous ESA paper. And finally, we need something called unique and consistent APSP. I will explain this item in the very end of this talk, but the main focus of this talk should be the first technique, adjoint of symbolic adjacency matrix. To start, let me tell you how to reduce the problem of computing DSO to the problem of computing R-truncated DSO. What is an R-truncated DSO? It's a DSO that returns the correct answer if the answer is at most R and returns R otherwise. Recall that we are dealing with unweighted graph, so shortest path, the distances are at most n, and you can think of R as some small polynomial such as square root of n. That is, we only care about the short distances. For the long distances, we don't care. In my previous ESA paper, I showed the following transformation. Suppose we have an R-truncated DSO with preprocessing time P and query time Q. Then we can bootstrap it to a normal DSO with preprocessing time P plus n square Q plus n cube over R and constant query time. So to obtain our main result, it suffices to construct an R-truncated DSO with the following parameters. The preprocessing time is R times n to omega, and query time is roughly R. If we could construct such a DSO, we can apply our bootstrapping argument to build a normal DSO with such parameters. And if you choose R wisely, you get some DSO with preprocessing time n to 3 plus omega over 2 and constant query time. If omega is 2, then this already breaks the n to 8 over 3 barrier. Let me also mention that this time bound of n to 3 plus omega over 2 is not optimal. We can use fast rectangular matrix multiplication to speed it up to somehow to n to 2.5794. Okay, so the main focus of the rest of the talk is how to construct such an R-truncated DSO. And we will use the so-called symbolic adjacency matrix. Let G be a directed unweighted graph. Actually, this technique also works for weighted graph, but we consider unweighted graphs for simplicity. Let Zij be random numbers. So the symbolic adjacency matrix of G, we call it SAG. It's a polynomial matrix. This means each of its entry is a polynomial over some formal variable x. On diagonals, they have the constant 1 as the entry. And for each edge I to j, we have a random number multiplied by x, which is a monomial of degree 1. So to give you a small example, this is a graph with 6 vertices, and the The symbolic adjacency matrix roughly looks like this. It has ones along the diagonal and uh, some degree 1 monomial for each edge. So we will consider the adjoint of SAG. For an invertible matrix M, the adjoint of M is the determinant of M times the inverse of M. The adjoint of SAG captures the shortest path information in the graph. There is a theorem that says with hyperability over the choice of the random Zij, for every two vertices A and B, the distance from A to B is the lowest degree of X in the AB's entry of adjoint of SAG. Let me still give you this example. We can calculate the 3/6 entry of adjoint of SAG, and the lowest degree of X in this entry is some constant times X squared. This means the distance from 3 to 6 is 2. The proof of this theorem is not very hard. Actually, every path from A to B contributes to the AB's entry of this adjoint of SAG. If the path has length L, then it contributes some constant times x to L to this entry. So if we want to find the shortest path from A to B, we simply find the lowest degree of x in this entry. Okay, then how do we use the adjoint of SAG to handle vertex failures? We need the following observation by a Fox 19 paper of Brand and Sarah Nurak. They showed that a vertex failure corresponds to a rank 1 update to SAG. That is, if you remove a vertex from G and compute the new symbolic adjacency matrix, then it's the old SAG plus a certain rank 1 matrix associated with X. And we can maintain the adjoint of SAG under rank 1 updates. In particular, we will use the following theorem. That says, suppose you preprocess the determinant of A and the inverse of A. Then, given a rank 1 update, you can compute the adjoint of the new matrix by this somewhat simple formula. Well, it's not simple, but you don't need to understand this formula. You just need to know there is a closed form for the adjoint of A plus a rank 1 matrix, and it turns out to be somewhat convenient to deal with. So let's construct an R-truncated DSO. Well, it's important that we only need an R-truncated DSO instead of a full DSO, and R is a somewhat small number. The preprocessing time should be R times N to omega, and the query time is roughly R. We use this theorem, and the preprocessing algorithm is simply to compute the adjoint of SAG modulo x2R. That is, we only care about the lowest R terms. The reason is that each path of length L becomes a monomial of degree L, and we only care about paths of length at most R. That is, we can modulo everything by x2R. Now, how much time do we need to preprocess? It takes N to omega arithmetic operations to invert a matrix. But now, in our case, each arithmetic operation is between 2 degree R polynomials, so it takes roughly R time. That means the time complexity is R times tilde O N to omega. Actually, this procedure can be accelerated by fast rectangular matrix multiplication, and the final trade-off turns out to be something like N to 2.5794. Now, given a query ABX, we want to find the shortest path from A to B that does not go through X. By the theorem, we want to find the AB's entry of adjoint of SAG minus X. We can write it as a rank 1 update to SAG. Then we invoke the previous formula, and we just need to compute the AB's entry of this thing. It turns out that we only need a constant number of arithmetic operations to compute this. So the query time is total R. In summary, we build the DSO using two steps. The first step is to build an R-truncated DSO via the adjoint of symbolic adjacency matrix. This step involves two ideas. The first idea is that adjoint of SAG modulo x2R encodes the distances in the graph up to R. And the second idea is that a vertex value corresponds to a rank 1 update to SA of G. We can easily maintain such updates and maintain the adjoint of SAG. So after step 1, we have an R-truncated DSO. Step 2 is to build an R-truncated DSO to a full DSO, which is essentially the same in my previous ESA paper. And if we set R appropriately, we obtain preprocessing time roughly n to 3 plus omega over 2. And if we use some rectangular matrix multiplication, the preprocessing time becomes like n to 2.5794. Now, I still have some time for the third technical point I mentioned. I'll only have time to tell you what the results are, but I won't go into techniques. So let me first tell you what the problem is. This problem is somehow needed in the bootstrapping step from an R-truncated DSO to a full DSO. That is in the machinery of my previous ESA paper. But in this paper, we will need a more efficient version of this thing. So we need a new algorithm. The problem is as follows. We have an unweighted directed graph. We want to compute incoming and outgoing shortest path trees that are consistent. So we want to compute n incoming shortest path trees rooted at each vertex and n outgoing shortest path trees, so 2 entries in total. By consistency, we mean that if there is a path from U to V in 2 different trees, then the 2 paths should be the same. Let me illustrate this by an example. We have a graph, and there are 2 shortest paths from U to V. One goes from the top and one goes from the bottom. Suppose we have already fixed the outgoing shortest path tree rooted at A. In this tree, the shortest path from U to V goes from the top. There are 2 possible incoming shortest path trees rooted at B. The difference between the 2 trees is whether the shortest path from U to V goes from the top or the bottom. So the top one is inconsistent with this outgoing shortest path tree because the path from U to V is different from the path from U to V in this tree. But the bottom one is consistent. So you get the idea. The problem is to compute 2n shortest path trees with this consistency requirement. So let me show you this is indeed a non-trivial problem. The naive attempt is to randomly perturb the edge weights. But well, the subcubic APSP algorithm relies on the edge weights being small integers. So if you randomly perturb the edge weights are no longer small integers, and it appears you need n-cube time to compute APSP. The second naive attempt is to somehow dig some shortest path trees from Zwick's APSP algorithm. Well, are they consistent? Anyway, I failed to prove they are consistent. Our result is that we can solve this problem in current APSP time. More precisely, we can compute in randomized n to 2.5286 time a consistent set of n incoming shortest path trees and n outgoing shortest path trees. So our result matches the currently best time bound for APSP. Okay, so this is our third technical ingredient. I believe this should be a fundamental problem, but however, I didn't find other literatures on this problem. I think there should be other applications of this besides DSO, and I would be very happy to find some. Let me conclude the talk by discussing some further directions. The first direction is whether we can match DSO with APSP. For directed graphs, we know how to construct DSO in N to 2.5794 time, but the current best time bound for APSP is N to 2.5286. So there is a very small gap there. It's roughly N to 0.051. But the gap still exists. So one problem is, can we close this gap? Well, I believe this N2 2.5794 may be somewhat inherent, maybe because of the way we use rectangular matrix multiplication. But of course, I'm not sure, and you shouldn't trust me because I used to believe the N2 803 barrier was inherent too. The second direction is to construct undirected DSOs in matrix multiplication time. Well, for APSP, for undirected graphs, APSP can be indeed computed in N to omega time. So it's natural to ask whether we can also compute undirected DSO in N to omega time. I could only say that the machinery in my previous ESA paper cannot give us such DSO. Maybe we need some new clever ideas. There are two drawbacks of our DSO. The first drawback is we don't support negative edge weights. This is not a drawback of symbolic adjacency matrix, but a drawback of the bootstrapping argument in my previous ESA paper. And the second drawback is that we can only report distances. We cannot find an actual path. This is a drawback of the symbolic adjacency matrix used in this work. I think it would be interesting to fix any of the drawbacks. That's all. Thank you for your attention.